The air intake of a gas turbine engine is either built into the airframe itself, if the engine is mounted in the airframe, or is the forward part of the nacelle installation if the engine is wing or rear fuselage mounted. The air intake is designed to provide a turbulence-free supply of air to the first stage compressor of the engine, with the minimum energy loss occurring through the inlet. To enable the compressor to operate satisfactorily, the air must reach the compressor at a uniform pressure, which is distributed evenly across the whole face of the first stage. Thus, the design of the intake duct is vital to the performance of the engine, under all air speeds and angles of attack, if compressor stall or surge is to be avoided. The simplest form of intake is a single entrance, circular cross-section, pitot type. The air normally flows directly through the intake when it's fitted to wing-mounted engines, but it can form an S-shaped duct when used on engines which are mounted at the bottom of the aircraft fin, for example like the Boeing 727 or the Lockheed TriStar, which are shown here. Crosswind takeoffs can cause the airflow through this type of intake to become unstable. The pitot type of intake maximizes the use of ram effect on the air due to the aircraft forward speed, and suffers only a minimum loss of ram pressure as the aircraft attitude changes. However, the efficiency of the pitot type of engine air intake reduces as the aircraft approaches sonic speed. This is due to the formation of a shock wave at the engine intake lip. The shape of a subsonic intake usually takes the form of a divergent duct. While the aircraft is moving at any appreciable speed, the divergence causes firstly a reduction of the airflow velocity between the lip of the intake and the inlet of the compressor, and secondly, an increase of air pressure at the inlet of the compressor. However, while the engine is running on a stationary aircraft, the pressure at the inlet of the compressor is below ambient pressure. This is because the engine compressor is increasing the velocity of the airflow through the intake. As the aircraft begins to move, the pressure within the inlet starts to rise. The ram pressure recovery point is usually reached at between Mach 0.1 to Mach 0.2. As the aircraft's speed increases even further, the ram effect produced by the speed increase, combined with the shape of the inlet, produces more and more ram compression, which causes an increase in the engine compression ratio. This effect generates more thrust without costing any increase in fuel flow. However, as can be seen from this graph, at these speeds the thrust recouped from the effect of intake ram pressure does not cause the net thrust level to reach its original zero speed level. Secondary air intake doors, sometimes called auxiliary inlet doors, are required on certain types of aircraft to allow supplementary airflow to reach the compressor face during high-power operation when that aircraft is either stationary or at low air speeds. The Harrier is an example of an aircraft which must use high levels of engine power when it has either zero or very low forward airspeed, during vertical takeoff, the hover, or landing. During these periods, the demand of the engine compressor for air is extreme. This particular engine air intake is designed for relatively high-speed flight, and as a consequence is not necessarily capable of allowing in the large mass of air the engine requires when it's running at high power levels at zero forward airspeed. To allow in more air to satisfy the engine demands, up to 16 auxiliary air intake doors have been fitted just behind the lip of the main air intake. At airspeeds below which ram pressure recovery can be achieved, the auxiliary air intake doors are held open by the depression in the intake. At higher forward speeds, when the pressure in the intake is greater than ambient, the auxiliary air intake doors are shut by the pressure differential which has been generated. Supersonic aircraft also require a particular type of air intake, which is sometimes called a diffuser, because the engine compressor cannot handle supersonic airflow. Below supersonic speeds, the intake must be able to recover pressure in the same manner as a subsonic intake. But above supersonic speeds, the intake must be capable of reducing the velocity of the airflow below sonic velocity by the formation of shock waves. One important characteristic of a shock wave is that air flowing through it will be slowed. The task of controlling the shock waves that form on or in the air intake, which is fundamental if we're to efficiently reduce the velocity of the airflow, is undertaken by a supersonic diffuser. The supersonic diffuser can be quite simple or quite complex, depending on a number of factors, among which is included the supersonic speed range of the aircraft. For instance, many jet fighters are not designed for sustained supersonic flight, and can therefore use quite a simple intake diffuser. Some of the earliest types of supersonic aircraft featured a central shock cone, called an inlet cone, which was used to form the shock wave. This form of shock cone can be seen here on the English electric lightning. This diagram shows a simple convergent-divergent diffuser. This design works because of the fact that supersonic flow will slow down as it enters a constricted area. You will note that this is the opposite response to that which happens with subsonic flow. Air flowing at subsonic speeds will accelerate through a constriction. We know from the previous lesson that subsonic airflow through a venturi accelerates towards the throat. At subsonic speeds, the air will maintain a constant density, and as a result a pressure wave is set up which causes the air to accelerate through the constriction. However, at supersonic speed, pressure waves cannot move out ahead of the air and cause it to accelerate. Therefore, the air becomes more dense and slows down. This is still all in accordance with Bernoulli's equation, which tells us that if the static pressure increases and the density increases, then the velocity must decrease in order to keep the total energy in the airflow constant. To most people, this tendency of supersonic airflow is more intuitive than what happens in subsonic airflow. The objective of the convergent-divergent diffuser is to slow the airflow to Mach 1 just before the throat of the diffuser. The subsonic flow thus obtained will then slow further as it moves through the divergent section, in fact slowing to well below the speed of sound before it enters the engine. Obviously, the geometry of the diffuser has to be specific to the speed the aircraft is flying. Therefore, if the aircraft is to fly at a range of speeds, some more complex system will be required. Generally, the convergent-divergent diffuser is only suitable for short bursts of supersonic flight, at less than Mach 2, such as on the F-15 fighter shown here. The engine air intake is designed to maintain a stable airflow to the compressor face. Anything that disrupts the airflow and causes it to be turbulent may cause the compressor to stall or surge. An intake operating at high angles of attack cannot be expected to maintain a stable airflow. One of the most critical times for any engine is during its acceleration to takeoff power. If there is any crosswind during the takeoff, it may affect the airflow into the intake, particularly in the case of aft body-mounted engines which have an S-duct type of intake. To avoid the possibility of engine stall and surge, the procedure defined in the operating manual must be followed. Typically for this type of aircraft, that procedure is to allow the aircraft to start rolling forwards on the runway with idle power set, before smoothly opening the throttles to have takeoff power set by approximately 60 to 80 knots. This procedure is termed a rolling takeoff. Intake icing will occur if the ambient conditions are conducive to it. Typically, these conditions are 1. An indicated outside air temperature of below plus 10 degrees Celsius, and 2. The presence of visible moisture, that is, fog or any form of precipitation, or alternatively, standing water on the runway, or if the RVR is less than 1,000 meters. In these conditions, the operator should select the engine anti-icing system. Damage to the intake, or any roughness inside the intake, may cause the incoming air to be turbulent, which may disrupt the airflow into the compressor, causing it to stall or surge. It's particularly important to inspect the engine intakes before flight for any form of damage, uneven skin panels, surface roughness, etc. Damage to compressor blades is invariably caused by ingestion of foreign objects. This will most commonly occur while the aircraft is operating on or close to the ground. Damage to the compressor blades leads to changes in their geometry, which can cause performance deterioration, compressor stall, and even engine surge. As well as ensuring on the pre-flight check that the engine intakes are free of foreign objects, particular attention must also be paid to the area on the ground in front of the engine intakes prior to engine start, to ensure that it's free of loose stones and other debris. This is particularly important in the case of wing-mounted engines, which have their intakes close to the ground. It's no coincidence that aft body-mounted engines, whose intakes are above the level of the bottom of the aircraft fuselage, suffer much less with foreign object damage than do wing-mounted engines. Heavy in-flight turbulence can seriously disrupt the airflow into the engines. Using the correct turbulence penetration speed will reduce the possibility of compressor malfunction. It may also be a requirement of the checklist in these conditions to activate the continuous ignition system to reduce the probability of engine flameout. To prevent damage occurring from foreign object ingestion, it's essential that the operators of gas turbine engines should take precautions which preclude the entry of debris into the ramp area. After flight, intake and exhaust covers should be fitted to prevent ingress of contaminants and also help to prevent the engine windmilling. During engine startup, aircraft taxi, and engine reverse thrust operation, debris can be sucked into the intake. Engine power should be kept to the minimum required to avoid damaging it.